Let's look at another example for chapter 1.3. Here we have just some rational function, ratio of two polynomials. What's the first thing you would do when confronted with a problem like this? You might graph it. That's not a bad idea. You might say, well, let me just try plugging in 0 and see what happens. So let's write that down. So try plugging in 0. And you end up getting 0 minus 0 over 0 minus 0. So you end up getting 0 over 0. So can we say then that the limit does not exist? And the answer is nope. So I'm going to put a box here and cross it out. Even though it's tempting to say, I tried something, I got an undefined or indeterminate thing, so this just fails. Remember, limits were invented or discovered, depending on how you think of it, to deal with situations where we get 0 over 0, like in difference quotients, but we think the answer really shouldn't be 0 over 0. It should be some other number that depends on the behavior nearby. So what we can do instead is try some algebra and see if we can avoid the divide by 0. So we're going to say don't give up if you get 0 over 0. Try algebra. So you might have noticed I've got factors of x here, so I could factor out an x, or not just an x. I could say my original limit is, I could pull an x cubed out of everything, right? So I can say it's equal to the limit of x cubed times 23x squared minus 11 over x cubed times 19x to the 1 minus 7. And then what does that suggest? Maybe canceling the x cubed, right? So we'll cancel those and say this is now the limit of 23x squared minus 11 over 19x to the 1 minus 7. And now let's try plugging in 0. And you get 23 times 0 squared minus 11 over 19 times 0 to the 1 minus 7, which is just negative 11 over negative 7. You could cancel the negatives, not too hard. So overall, we did not get, we started out by seeming to get 0 over 0. We persevered, and we did not end up with an answer of 0. We didn't end up with an answer of infinity, which you might guess when you're dividing by 0. We did not end up with an answer of 1, which you might guess if you see something over itself. We ended up with something that was determined by the numbers going on in the problem. You might also notice that what if I hadn't had an 11 up here? What if I had had a 12 or a 93 or a 300 million or something? That would have just carried all the way through, and we would have gotten that same number here. So whenever you see a 0 over 0, it's called an indeterminate form because it's just not enough information to figure out what the final answer is going to be. You really need to try some algebra and use that to figure it out. So we can't just say 0 over 0 is 0 or infinity or forever undefined. This limit is defined, the limit does exist, and the limit is equal to 11 over 7. Some other things to notice here. So we started out with a limit problem, and then we said that's equal to the same thing written this way. This would still have the same divide by 0 problem if I plugged in a 0, right? Because I'd get 0 cubed times something, so I'd have a 0 denominator. So this and the original are exactly equal to each other. The fractions are exactly equal to each other for every x. But by the time I get here, I don't have a divide by 0 problem. So I actually need to justify the step from here to here. So it's that equals right there that is justified by what limit property? You could call it the matching functions limit law, right? Functions that are equal at all but one point, and that one point is when x equals 0. So I have to say going from there to there is justified by the matching functions limit law. And then going from here to here when I'm plugging in 0 and getting a perfectly well-defined fraction, notice I'm not writing the limit anymore. I've already taken the limit at this point, so I don't write the word limit here. So let's write here, don't write limit anymore. I've already kind of conceptually taken the limit. Right, so that's some tips on the technicalities. What I would do at this point is then go double check by graphing it. One other thing about the matching functions limit law, let's say I had a problem, something like limit of, as h goes to 0, of something like 7 cubed minus blah 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 blah, and then minus 7 cubed over h. You might say, hey, let me cancel the 7 cubes, right? So we'd come along and cancel those out. The positive 7 cubed here, the negative 7 cubed there. And then I'd say this is equal to the limit as h goes to 0 of whatever all that stuff was. I don't need to cite the matching functions limit law because this fraction and this fraction are exactly the same everywhere, even at h equals 0. They're both undefined at h equals 0. I've only canceled stuff in the numerator here. So I don't need to cite the matching functions limit law because the numerators are the same function at all h's, even when h equals 0. Since the numerators are the same function at all h values. Even at h equals 0. All right.